This lecture is going to be on limiting reactants. So far in this course, we've looked at reactions in which all of the reactants are consumed in a chemical reaction, and we've calculated how much product could you make from a reaction. But one of the things that's really common in chemistry is when we perform a reaction, we don't actually mix the chemicals in the stoichiometric ratios that this balanced reaction shows. And when this happens, it means one of the reactants is present in excess, and that not all of it will get used up. And then the other reactant will be called the limiting reactant because it will all be used up. And because once it's gone, we can make no more product, it'll limit the amount of product that can be formed. So let's look at a couple examples of this. And we'll look at an example, and we'll look at this simple example for the formation of a molecule that's known as ethylene glycol, also known as antifreeze. And when this reaction is performed, we take this molecule here, ethylene oxide, and react it with water to form ethylene glycol. So this is the molecule we want. In the lab, when this is done on large scale to make antifreeze, water is cheap, but ethylene oxide is expensive to make. And so we want to make sure all of this gets used up and none of it is left over. In other words, all of this goes to product, and if we have extra water at the end, that's fine. So what we do is we use an excess of water, right? So we have more water in the reaction than we need. We can see it's a 1-to-1 ratio, but in reality, we're going to have a lot more water present than ethylene oxide. And so we say ethylene oxide limits the amount of water that we can make, right? So that is our limiting reactant. And that's the general idea of what this limiting reactant means. We can show this pictorially. So here's your water molecule. Here's your ethylene oxide. You can see we have one. I'll circle them for you. We have 1, 2, 3 ethylene oxides, and we have 1, 2, 3 that would react with those, but we also have an extra water here and an extra water here. So after the reaction, we have 3 product molecules, but we see we have these 2 water molecules left over. We have an excess amount of water. We've used up all the ethylene oxide. When we think of these limiting reactants, a couple things to take note of. The balanced chemical reactions tell us the mole ratio of how things come together. That's not the ratio in which we add things in a lab. That's just the ratio of how they react. So most of the time, we're not actually going to mix things in their stoichiometric coefficients. Most of the time, we will have a limiting reactant, which limits the amount of product that can be made. So there's only one limiting reactant, and then there might be one or more excess reactants or reagents, and these are the ones that do not fully react. So if we want to figure out how much product we can make, we actually have to figure out what the limiting reactant is first. And the best way, there's a couple ways to do this, but the best way to find the limiting reactant would be to go through the calculation with each reactant quantity that's present and calculate how much product could we make. Whichever one makes the least amount of product, that's your limiting reactant, and that's the maximum amount of product you can make. So let's look at a fun example, and then we'll look at a chemistry example, or a more fun example, if you will. So let's pretend we're working in a sandwich shop, and we're going to make some sandwiches. So we have our specialty sandwich shop, and we only make one type of sandwich, a grilled ham and cheese. All right, so the recipe for this calls for 2 slices of bread, 1 slice of cheese, and 3 slices of ham. Now, one way we could write that recipe is as a balanced chemical equation, and that would look like this. 2 slices of bread plus 3 slices of ham plus 1 slice of cheese goes to 1 sandwich. So we need all of this to make 1 sandwich. So if you work in the sandwich shop, you might come into work one day and find out that all we have in stock are 8 slices of bread, 9 slices of ham, and 5 slices of cheese. So the question becomes, how many sandwiches can we make, right? So this is a limiting reactant problem, right? We're going to look at this and say, this is the recipe, this is the chemical reaction, and this is what we have to mix together. So how many total sandwiches can we make? And you might be able to do this quickly in your head, but let's go through this and pretending it's a chemical example so we can build how to solve this problem. And what we're going to do is we're going to start with each reagent or each ingredient. So 8 slices of bread, 9 slices of ham, and 5 slices of cheese. And we're going to ask ourselves, how many sandwiches can be made from each ingredient? So if we have 8 slices of bread, how many sandwiches can we make? And the way we would answer that is with a mole to mole ratio. So 8 slices of bread, right? This is what we have. And then a mole to mole ratio, 1 sandwich for every 2 slices of bread means we can make 4 sandwiches. If we have 9 slices of ham, we're going to do the same thing. Again, do our mole to mole ratio. For every 1 sandwich, we need 3 slices of ham. So 1 to 3. So those 9 ham slices can make 3 sandwiches. And if we have 5 slices of cheese, our recipe says a 1 to 1 ratio. So that means we can make 5 sandwiches. Now we can't make all of these sandwiches, but what we'd say is the ham limits us. We can only make 3 sandwiches based on the ham. Ham is our limiting reactant, right? Ham limits the amount of sandwiches we can make. So we can only make 3 sandwiches, which means we're going to have extra bread left over, right? Because we'll only use 6 slices of bread, so there's going to be 2 extra slices of bread. And we can only make 3 sandwiches, so there's going to be 2 slices of cheese left over. So the bread and the cheese in this case are the excess reagents. Okay. Let's go through a chemical example. And let's imagine a reaction where we were mixing 10 grams of carbon monoxide and 10 grams of oxygen, which combine to form CO2. And the question is, how many grams of CO2 can be produced and how many grams of the excess reagent remain? So when we start with a problem like this is a stoichiometric problem, it's a limiting reactant problem, we always start with a balanced chemical equation. So we'll go ahead and balance the chemical equation, and we find out we have 2 COs plus O2 goes to 2 CO2. The next thing I'm going to do is I'm going to take our masses of reagents, 10 grams of each, and I'm going to convert them to moles, right? Because we're dealing with a balanced chemical equation. We need mole to mole ratios. So I'm going to go ahead and convert both of these into moles. And we get 10 grams of CO divided by its molar mass gets 0.357 moles of carbon monoxide. And then we have 10 grams of oxygen divided by molar mass, we get 0.313 moles of O2. What we're now going to do is use these moles to figure out how much CO2 they could make if they all reacted, right? So we use the mole ratios to determine how much product can be made by each, just like we did in our sandwich example. So we'll start off with the CO. We take 0.357 moles of CO, and the key for all of these, right, is your mole to mole ratio. So in this case, it's 2 to 2, and that comes from 2 to 2. And then we do the same thing for our oxygen. And again, in this case, we have a 2 to 1 mole ratio, and that came from 2 to 1. So we can see if all of the CO reacts, we can form 0.357 moles of CO2. If all of the O2 reacts, we can form 0.626 moles of CO2. So we can't make both of those. We can only make the one that gives the least. So carbon monoxide, right? Carbon monoxide is our limiting reagent, and that will be completely used up, leaving some oxygen behind. So this is the amount of product that we will make. Now, how many grams of the products are produced? If we want grams, we now know the moles of CO2 that were produced from our limiting reagent. So if we want to go to grams, we can just multiply by the molar mass, right, of CO2 to get 15.7 grams of CO2. The next question says, if not all the O2 reacts, how many grams of O2 remain? Well, how do we find this out? First, we have to figure out how much O2 would react. And we can do this now. This is a similar stoichiometry problem to say, we know how much carbon monoxide reacts, all of it. And so we just have to ask ourselves, how much O2 will react with that much carbon monoxide? And so that's going to look like this, where we start with our moles of carbon monoxide. We're going to do our mole to mole ratio. And then in this case, I just went straight to grams using the molar mass of O2. And we find out that this is the grams of oxygen that react. Now notice, we started with 10 grams, we reacted 5.71 grams. So if we want to figure out how many grams remain, we just subtract the two. And we find out that 10 minus 5.71, we have 4.3 grams of oxygen left. Thank you.